Hello everyone and welcome to a video on electrical energy. So the story goes that in 1752 on the 10th of June, Benjamin Franklin went out to fly a kite during a thunderstorm. He did not do this because he lost his mind. He did this because he was conducting an experiment. The aim of his experiment was to capture electrical energy and place it within a jar. He would do this by attaching a metal key to the string attached to a kite, and so when the lightning hit the kite, it would move through the string into the key, and then he would place the key that would supposedly capture the electrical energy from the lightning into the jar. What he found was that when he reached out for the key, a spark moved from the key into his hand. And this fundamentally changed our understanding of the nature of electrical energy. Because before then, or before this experiment, there not much was known about electrical energy at all. So this experiment set in motion lots of research and our understanding of what electrical energy is to the point of what it is today. So before Benjamin Franklin's experiment, and before electrical energy was used in homes, so as electricity, life was very different, right? If for one, there was no light bulbs, so light was generated or emitted by kerosene lamps, so basically burning a fuel. In fact, that was the approach for many things, and because there was no electrical energy, there was no running water, there was no indoor plumbing, so forget about showers, forget about taps, forget about um, warm water as well. Don't forget about hot water. You would have cold baths, right? Everything would be very different. The once your food was cold, you wouldn't be able to warm it in a microwave. So all those things that we enjoy today, all those luxuries, was not even imaginable in those days before electricity was used. So um, next time you're on a phone or as you're watching this video or enjoying electricity, right? Whether it be having enjoying warm water or you know being able to do number one, number two in your house and not outside, just right. Remember that Benjamin Franklin did this experiment, and thanks to him, we got to this point. On a side note, though, I just want to say that I'm not saying that Benjamin Franklin did everything for electricity. He just did a very small part, right? He just basically, uh, you know, sparked the idea, or the interest. But it was actually Michael Faraday, who's known as the father of electricity, and not Benjamin Franklin. So thank you, Michael Faraday, for all your contribution to what we know about electricity today. So, what is electrical energy? Electrical energy is generated by the movement of electrons between atoms. Now, before we go any further, we first need to understand the structure of atoms. So, if I take the simplest atom, which is the hydrogen atom, we'll see that it has a proton at the center, which is found in the nucleus, and it has another energy particle called an electron that orbits around the outside of the atom or around the atomic nucleus where we find the proton. And it's important to know that electrons have a negative charge, or they're charged negatively, they have a negative charge. Protons have a opposite positive charge, all right? And then you'll see that there's also a neutron, which you don't really need to know about. But neutrons have a no charge, but they don't play much of a role in what I need you to understand about electricity right now. Then if we take a look at carbon atom, we'll see that it has 6 times as much electrons as protons as the hydrogen atom. So you'll see that it has 6 electrons, right, floating or orbiting on the outside of the atomic nucleus. And you'll see that there are 4 pluses, but there are actually 6. You just don't see the other 2 that are maybe hidden behind the neutrons. But there are also 6 protons to match the number of electrons. And this is very important because a neutral atom, so an atom that is balanced or neutral, will always have as much electrons as it does protons. And why is this? And this is because of the law of charges. And it's also what we need to understand before we understand how we get electrons to move in the first place. So we need to remember the law of charges, and that is that like charges, that means charges that are the same, will repel each other, which means push each other away, and opposite charges will attract each other. And we can see that in the image here to the right. We see that a proton and electron will attract each other, right, pull each other closer, and a proton will repel each other, and so will an electron and electron. They will push each other away. And this explains, or this basically helps us understand the structure of atoms. So you'll see that this is the relationship of attraction between a proton and an electron, and this is also why for every proton you will also have a matching electron, and for every electron you will have a proton that is there attracting it. And this is the law of charges, is why atoms will always have as much electrons as they have protons. And on a side note, if this looked familiar, it's because this is exactly how magnetic fields look, and there's a reason for that, but I'm not going to cover it in this video, maybe in another video. Right, so getting those electrons to move, well, the first way is through friction. And when we do this, we usually create something, a type of electrical energy called static electrical energy, which is one of the two types of electrical energy we need to know about. Static electrical energy is when electrons are pulled from their orbital through friction, and they gather, but they do not flow. And you can see that in this example here to the right. We see that in the beginning, we have a neutral rag and a neutral pipe. That means that both the rag and the PVC pipe, the plastic pipe, have as much electrons as they have protons. But once we rub them together, you'll see that the rag loses its electrons to the pipe, causing the rag to become positively charged and the pipe to become negatively charged. It's also important to know that the rag doesn't lose all its electrons, because that would be impossible. What does happen to the rag is that it loses some of its electrons, especially at the surface of the rag, and those electrons are pulled towards the pipe, and the pipe becomes overall negatively charged. So the pipe has more electrons than it has protons now, which means that it has a overall negative charge, and because the rag has more protons than it has electrons now, it will have a overall positive charge. And that's just how static works. Yeah, that's it. It's in a nutshell. So that's static electricity. That's how static electrical energy is created, and you'll see that the law of charges takes or plays a part here in static as well. So because the side of the balloon that is negatively charged is attracted to the side of the wall, or the surface of the wall that is positively charged, right? Because of that law of attraction between oppositely charged particles, or oppositely charged, or objects that have a opposite charge. And you'll see that the balloon surface that is positively charged repels the other balloon surface that is also positively charged, because like charges repel each other. It's important to note that static electrical energy is not forever, because once two charges that are opposite, once two surfaces that have opposite charges come into contact, those electrons will move back towards the positively charged atoms, and basically find space where electrons missing, and those atoms that are positively charged will then again become neutral once they have as much electrons as they have protons. The effect, or that behavior of the charges moving or being attracted to each other, and repelling each other, we can see in a more dramatic way if you look at how static electrical energy forms in clouds. So in clouds, when the raindrops in a cloud rub against each other, they form a difference in charge. So from the movement, the electrons are pulled, and this causes the cloud to develop two separate charges, where the top of the cloud will become positively charged and the bottom of the cloud will become negatively charged, for instance, right? Not always, but just for an example. And what happens is all these electrons gather here at the bottom of the cloud, and because there's so much electrons gathering, it becomes like very negatively charged, and the ground becomes positively charged, and so this creates a very strong electric potential between the cloud and the ground. And eventually what happens is those electrons will have enough, there will be enough potential to cause them to actually flow or move quickly through the air uh, into the positively charged ground to regain or reestablish that neutrality, and then have a neutral for there to be no charge anymore. So the more difference in charge, the stronger the electric potential that is created. And we can see that it's not just from clouds to ground, but also from the bottom of the cloud to the top of the cloud that is positively charged, or from clouds that are different clouds that are have different charges as well. All right, and that brings us to our next type of electrical energy, which is electrical current, because lightning is not static. Lightning is actually the flowing of electrons, which is electrical current. So, electrical current is when electrons flow, and when they flow in the same direction, this creates an electric current. And we can see that in the image here. We see that these electrons move from one atom to another in one direction, which is electrical current. Now, how do we get electrical current? Well, before we can have electrical current, we must have voltage. And voltage is symbolized with a capital V. So, what is voltage? Voltage is also known as electric pressure or electric potential. We call it electric pressure or electric potential because it creates a potential, right? It creates that pressure needed for electrons to move and then get work done. Another way to think about electric potential or voltage is to think about or to compare it to the force of gravity. So if we take, for example, water standing at a height, uh, gravity is basically is pushing down on that water, right? The water is being influenced by the force of gravity, the gravitational potential, and once we open a valve or the pipe, the water will fall down. The height will fall all the way down until it hits a ground or the lowest level of the pipe system, and then that energy, that kinetic energy generated from the fall, will then will then carry on through will push the water through the pipe. So the higher the water has to fall from, the higher the height the water falls from, the more kinetic energy it has as it goes through the rest of the pipe. In the same way, the higher the voltage that is in the circuit, the more energy the electrons have as they move through the circuit. So the higher the voltage, the more energy the electrons have, right? It's basically the push force the electrons have to start moving. And once they have that force, they will use the energy that they gain from the voltage to make their way through their pathway until they run out of that energy. So as long as you have voltage, you will always be able to move those electrons. So in an electrical circuit, voltage is provided by a variety of components, um, mainly electrical cells, like this one here, batteries, which is when you have two or more cells connected together, and generators like this commercial generator, but also those large generators they use in power stations, which pumps out can create a large or a very powerful voltage. Right, and then lastly, we're just going to look at how voltage creates an electric current in a circuit, in a simple series circuit. You'll notice that when the switch is open, the electrons don't really have a direction. They kind of just move in they don't have a direction. They just move everywhere randomly. But once we close the circuit with the switch, once the switch is closed, you'll see that the electrons now move in one direction from left to right. And this is because the negative charge by the negative terminal of the battery is creating, along with the positive charge on the opposite side, is creating that electric potential needed for these electrons to start flowing and create an electric current. And then I want you to take a look at this device here. It's called an ammeter. It actually measures the magnitude or the power of, not the power, it measures the amount of current, the strength of the current. And you'll see that when the switch is closed, there is a current because that's when the electrons are actually flowing through the wire. Just an interesting way to look at it. Another thing that before I close the video, I just want to draw your attention that The reason why this can happen at all is because this wire, this blue wire here, is actually a conductive material, probably copper, which is why the electrons move randomly by themselves, even if there is no voltage. But what the voltage does do is it allows them to move in one direction so that work can be done, so that a light bulb can glow, so that a motor can turn, so that a buzzer can buzz, right? And that's the difference, and that's why we need a voltage so that we can have a one direction of flow for these electrons, right? I hope you found that helpful, and please drop a like if you enjoyed the video. And if you haven't subscribed yet, please do so. There's still much to learn, and there's much more videos coming on the way. Stay awesome. Till next time.